Cool. Hi, everyone. I'm Jake Hillion. I was hoping to present this with Johannes Bechberger, but he hasn't quite made it yet due to Deutsche Bahn delays, mainly. But he should be here, hopefully, by the end to say hello. We're here to talk today about a side project we've been working on involving concurrency testing using custom Linux schedulers. I work at Meta, and I work on schedulers, mainly custom Linux schedulers. So this is pretty related to what I do. Johannes is an OpenJDK developer who recently had to spend a lot of time debugging a race condition. So we hope we could put those two things together, and we've got a bit of a proof of concept today that we can show you and explain how it works to attempt to make these a little bit more likely to occur, which should make them easier to debug. So, Heisenbugs. I imagine lots of us are familiar. You've got the same input, you hope for the same output, but instead you get a crash. This is not great. And it's especially not great when it happens 1 in 10,000 or 1 in 100,000 or 1 in a million invocations. As an application owner, debugging that from reports is very tricky. We'll go for a simple example now. Very simple because these things get complex in reality. But imagine we've got some data being produced from a producer thread and we're consuming it in a consumer thread. In our case, and in our example later on, there's an explicit expiry date on that data, which isn't what really happens in production. More likely, you've got some reference to a pointer that you might clear in some other thread. All of these expiry reasons that data might no longer be valid at some point in the future. It doesn't crash the vast majority of the time. The reason for this is that schedulers are pretty good. But when that interaction happens, when your machine gets a bit busy, when some processes get in the way that you weren't expecting, when the network gets slow, all of these things can just add extra delay. So a large reason for these conditions is scheduling. We see this, for example, RR, the debugger, has a chaos mode that's supposed to make these a lot more likely too, but that has its own issues. What is scheduling then? What do we actually do? In this case, we're talking about CPU scheduling. It's one of the more common types. The problem we've got many processes, likely in the order of thousands, and some number of CPUs, likely in the order of tens nowadays. And we need to somehow make sure all those processes work successfully on that CPU to share the system. The simplest way we might do this is just to schedule process A, and whenever it stops, we'll schedule process B. Unfortunately, that really does not work. There are classes of non-preemptive schedulers. Sometimes it makes sense, but the vast majority of the time we're going to need to schedule B a bit sooner, or the issues we were talking about before, they'll happen more often, network timeouts, all that sort of thing. So instead, we go over time and we'll stop scheduling A for a bit. B might not be ready the next time. We might schedule A again. We'll schedule B, we'll schedule A, we'll flip back and forth, and we're doing this on the scale of many thousands of processes, likely with several ready at any point in time. On an actual system, it might look something like this. We're not going to be able to look at any of the detail on this chart, but on the left, in the y-axis, we have which CPU we're looking at. As we go across, we're looking at what's happening on that CPU, whether a process is scheduled, the different colors, the different processes, and it all gets quite complex. But these sort of charts, super interesting. This is a 612 Linux system just running eBPF, the default scheduler. We can see processes are darting around all over the place. They're coming in, they're running for a short time. Some of them are long running, they move about a bit. There's all sorts of complexity, and this is even on a pretty quiet system. When you start looking at big systems, hundreds of CPUs, the interactions just get way more complicated. So when we look at our race conditions, you're replicating this on your lovely dev machine. You've got a 32-core processor. It's nice and quiet. You don't want anything getting in the way of your testing. The bug never happens, ever. It's a nightmare. You know it's happening. People are reporting it. You're running the standard scheduler, and the bug never happens. You can try running stressors in the background, and that might make it a little bit more likely, but the bug still never happens. Working on custom schedulers at Meta, I got to work with some schedulers that are not too good, which is great. It turns out when you write a scheduler yourself and you add loads of configuration options, there are many ways to configure that scheduler badly. And I found one a little while ago. I was working on a service, I was writing a scheduler, I got the configuration terribly wrong, and the service failed. It really didn't work. But there were 3 parts to this service. 2 of them hit massive timeout errors, but they came back to life. 1 of them crashed. So 250 hosts died all at once because of my scheduler. It turns out this was a race condition. Someone was storing the value of a shared pointer instead of copying the shared pointer in C++ for efficiency reasons, and they got it wrong. So if there was a long enough delay in scheduling, the service would crash. This does happen in the real application, but it's so rare that nobody would ever look at it. Or even if you did, you would really struggle to replicate it. So what if we wrote a scheduler that was deliberately bad? What if it was deliberately erratic and got us into these states more often where these errors are likely to happen? That's what we've got a demo of today, but how would you write an erratic scheduler? Well, there's some options here. You could write it in the Linux kernel. You might have a hard time doing that in general. The scheduler is very sensitive. If you get it slightly wrong, your system will hit the soft lockup detector and immediately reboot, which is a bit of a pain. It's hard to do. If you get it wrong in memory unsafe ways, your system will crash even more quickly. And if you get it right, you're still waiting, well, maybe in the tens of seconds for a kexec every time you want to change your kernel. This is a bit awkward. Nowadays, we can do it in user space. Johannes likes to talk about Java. He's got a project that I'm not going to give enough credit in this presentation because I don't know enough about it, where you can write these schedulers in Java. I'm more familiar with the Rust ones. You can also do it in C, if that's what you like to. And it's all because of BPF, which is the B, SCEDEXT, which is the, I think we're supposed to call it a sextopus, which is an interesting choice of logo we got there. And then this is the additional logo on the right. This is a photo of Brendan Gregg supposedly shouting at hard drives, but there's a quote about putting JavaScript into the Linux kernel here. Many similarities between the eBPF, the way it runs in the kernel, and a virtual machine for JavaScript you might have in your browser. Here's a photo of him looking slightly more normal. I think he'd prefer that one. eBPF. We're not going to go into it. It's not super important how it works, but there are a few details that we need to cover just for the understanding. When you develop an eBPF program, you're going to write your source code in some language. There's a few options we have. C's the standard one. Rust works reasonably well. There's some sort of academic languages you can choose as well. And then there's the Java transpiler that Johannes has got, which is quite exciting. You compile that into BPF bytecode. It's like assembly. But it's its own language that works on all the Linux systems effectively. We make a syscall to BPF to ask it to load our program into the kernel. You need a lot of privilege for this. It's a root-only operation again now, I think. It kind of got user for a while, but now it's all root. It goes through the verifier. The verifier is a magic black box that's supposed to make sure your program is safe in certain ways. So you can't read memory in a bad way that will cause your system to crash. You can't have unbounded loops that don't terminate because we're running this in the scheduler hot path. If you have non-terminating code there, you're in trouble. Stuff like that. It's a bit of a beast to work with. But once you're verified, you get JIT compiled, loaded into the kernel. You can look at sockets, network interfaces, scheduling now. You're loaded as an x86 program. There's no, or ARM, whichever system you're on. There's no further runtime basically attached. And then you communicate with that, mostly using syscalls at the minute. We're getting some new stuff called arenas, which are more like map memory, and you can communicate back to user space. So we can write an application across user space and kernel space, which is pretty cool. So the general way we write our production schedulers is we write some Rust that talks to the BPF, and then the BPF runs in the kernel and makes quick scheduling decisions. So that's BPF. How do we use that for scheduling? Recently merged in Linux Kernel 6.12. We're now on 6.13, so it's pretty recent. SCEDEXT, it's the extension framework for jumping in as a scheduler from BPF space. This is Tajan, the creator. There's a few key features. I mentioned some of the troubles with working in the kernel before, and the idea is that SCEDEXT makes them better. It doesn't make them perfect, but it certainly makes them better. So ease of experimentation, we have a repo with in the order of 10 schedulers now, maybe a few more. The Linux kernel has 2-ish schedulers. Even the old one had to be ripped out to make way for the new one. So we don't have a lot of optionality in the kernel, but you can run many different SCX schedulers on your machine, switching between them just by running a program and pressing Control-C. It's super easy. Customization too. We can talk to user space. You can do basically anything you want in these schedulers. Sure, some of it has to avoid the hot path, and you've got to communicate with user space a little bit. Turns out that's not as bad as we might think. But you can make loads of choices. You can use information from NVIDIA SMI that the Linux kernel is never going to do, and stuff like that. And finally, rapid scheduler deployments. Deploying a new kernel at scale is tricky. We have to get it to millions of machines, and it takes in the order of weeks to get that kernel out. Deploying a new scheduler can take a day. It's really easy, and running it and stopping it is also easy. You don't have to reboot. So if we find out weeks later that our scheduler is kind of bad, we can just stop it and we go back to the default, and everyone's safe. We don't have to worry about how much we've broken all the systems. In the SCX scheduler, again, maybe don't worry too much about the details, but we have a few bits that we have to worry about. On each CPU, we have a local FIFO queue. It's just first in, first out, and that's effectively read from by the kernel. If you've put stuff in that queue, the kernel side of SCX will make sure it gets run on that CPU in that order. Quite convenient. In SCX, we generally have global queues as well when we write our own schedulers. In this picture, we've got one. You can have a dozen. You can have as many as you like. And within those queues, you can mean different things. So on some schedulers, we might have a different queue per LLC. Some schedulers, we have a different queue per how much we want to prioritize the workflow, and various different things like this. The scheduler's job that we write in SCX is to move things from global queues into local queues and accept new processes, make decisions based on them, and let them run in the order we like. To view a super simple scheduler in the Java side of this framework, first step is to license everything as GPL. That's an absolute requirement with BPF, which is pretty cool. License it as that. We're going to share this constant of a shared DSQ ID, nice and easy. We'll create a shared DSQ, which we need to be able to handle tasks in a more uniform way. Handling it per CPU would end up with separate scheduling issues. So we'll create that DSQ, and now we've got our queue, and that's it. Next one, enqueue. This happens when you receive a task that is now runnable. You've got a task. Ideally, you want to put it on a CPU, but if you can't put it on a CPU, we're going to enqueue it. In this case, we're using another kfunc SCX BPF dispatch. We're taking our task, we're putting it in our shared DSQ. We're saying next time it runs, it can have up to 5 milliseconds, and then we're just passing through these flags. It's pretty simple too so far. And the final one is dispatch. This is what's called when a CPU goes idle. You have your CPU, it's finished doing whatever it was doing, it doesn't know what to run next because its little queue is empty. So we just run SCX BPF consume from the shared queue, which takes the task from the shared queue and just runs it on that CPU for us. That's it. That's a whole scheduler. It's not a very good scheduler. We're using FIFO queues everywhere. There's no priority for any processes. Everything is completely equivalent, which it turns out doesn't work very well. And there's also only one global queue, so if you're on any sort of complicated CPU, that will really struggle. If you've got 2 sockets on certain Intel machines, this will kill the machine because their cross-socket communication is so slow that if you try and run the scheduler, you hit the soft lockup detector before the SCHEDX thing can get kicked out, which is normally very safe. Normally, SCHEDX, if you don't schedule stuff, it just gets kicked out and you go back to normal. But the Intel machines are so slow, you can't actually get kicked out because that bit of kernel code can't run in time. So that's quite interesting. But in the general case, you're pretty safe. This will run, and then you can extend it as you like. Producing erratic scheduling orders. That's what this was all about. How can we make our race condition far more likely? We have let's see. Let's go, first of all, this is the example. We have an example here written, I believe, in Java again. It's a super simple thing to crash. We just consume things from a queue that are only valid for a certain amount of time. It's missing a little bit of the code here, and I won't find it because you always need a bit of plumbing to make these things work. But effectively, we get a task come from this producer thread. We've set a time on it that's just a limit, and if we try and read it beyond that, we're going to crash. And then we just keep reading it. On a quiet system, this is fine. This will run for days at a time, and it will never crash. Even on a busy system, we haven't yet seen a crash, but it can theoretically happen. We had to get quite simple with these examples to make them fit, basically. I've got a video to show you from Johannes that I'm going to have to talk over, I believe. There we go. Okay. So we started our scheduler. We've got scheduler.sh, which just launches our scheduler with the correct arguments. Samples runqueue.sh. Here's our sample script, the Java I just showed you, and we're getting some extra verbosity out of it. Every time we make a scheduling decision, we're printing it here. And the way we've set this up is it's going to sleep things for just way longer than it needs to. We'll take runnable tasks that would get a CPU immediately on a normal scheduler and not schedule them for whatever amount of time this is saying. So this is going between kind of half a second and a second and a half of not scheduling a task that could be scheduled. Then when it runs it, we run it for 80 milliseconds, something like that, and it normally finishes. And we saw it crashed, which is pretty good. This program, again, hours at a time, we've left it running on these machines. It doesn't crash. It just never hits these edge cases. But those edge cases are there, and they can be hit. And if you scaled this sufficiently, if that thread with the random delay was actually a network request, and then your systems got slow, there was queuing on those, this would crash. So we've got a lot of times where this could happen. If someone reported it, you wouldn't be able to debug it comfortably on your machine. And that's it. We got a crash. I think we've got a few minutes where I can briefly scroll through the code. There isn't too much of it, surprisingly, again. Let's go. So we go back to... I take it back. Before I do that, have we got any questions?
Are you running this in some kind of CI or just for like local testing?
So the question was, are we running that in the CI or just locally at the minute? At this point, this is very local. It's quite constrained, this scheduler. It only works on small machines at the minute. We use a lot of those FIFO queues. It's very new, it's very early. What we were excited about seeing was whether we could make it crash, and we can. So the next steps with this would be to productionize it a bit more, get it able to run on a big service. Like that example I mentioned earlier, if I tried to run that machine, it's one of the new AMD chips, so it's got loads of LLCs, it's all a bit complicated. If we try and run this scheduler on there, it just doesn't work. It gets kicked out. The machine survives, but it doesn't work. So we need a more complex hierarchy in the scheduler, and then to interject the randomness. We also need some seeding and bits like that to try and get it more consistent, and probably a bit of searching too to find the right conditions to make it crash. So this is still very early. We'd be happy about contributions too.
Have you tried it on ARM machine?
Have I tried it on an ARM machine?
Yeah.
No, but it does work.
Oh, okay.
So SkidX in general, we have tried on ARM machines. It works fine. There's nothing super worrying about it, which is great. Yeah, we're a bit concerned. We've got a lot of ARM to cover at the minute.
What kind of things can you do from the scheduler? Can you look, for example, into the process memory to see, like, oh, it has, for testing purposes, it has these kind of bits. Now I know that I have to schedule it to give the CPU slice to another process, or
Yeah. So the question was about looking at the memory of the processes and what more information we can use from them to make a scheduling decision. That's super interesting. We haven't looked at that yet. We can do the filtering at the minute is based on parent PIDs effectively. So we were a little bit, the way we're running the scheduler is we schedule the whole machine, but we only care about messing up this specific process because otherwise we'll start finding race conditions in the shell and then we'll be in trouble. So the reason we do it like that is just easier. We use ppid at the minute. You can filter on, in other schedulers, we filter on things like COM, process name, thread groups, all these things. So but I've never seen the option of actually looking at process memory. That's super interesting. We are doing some stuff where the application can tell the scheduler what it wants in a more fine-grained way. Currently we just use niceness, which is a bit weak. It's not very rich. So we're doing more communication from the process to the scheduler in our production schedulers. And I think that would be possible here too. We're running in eBPF. It's full root privileges. You can kind of do what you want, which is cool.
You mentioned seeding a minute ago. When you actually hit a crash, do you have anything to help you sort of reproduce the same?
It's an excellent question. The question was about reproducing the crashes and how we can make that happen. The answer at the minute is no, we don't have that. It's a lot of the goal of this project, but when we were running through it, we started looking at how we could build this scheduler to get rid of a huge amount of the non-determinants in the process. The way we saw with scheduling it, we were going to slow it down too much if we tried to get rid of too much of the non-determinants. Because we want to be in the position long term where we can run this on production applications without slowing them down to the point where they stop serving traffic. And that meant we made some compromises. The main one is we schedule things on cores pretty quickly now, when the original plan was to go 1 thread per process, but it just isn't scalable at that point. So there's definitely some work to be done to getting this seeded and making it more reproducible. Yeah.
I was wondering about the scheduling points where you can decide to make the schedule. Sounds like only when the process goes to the kernel is the points that you can really do the scheduling, but if you have some bug, let's say, you increment a variable, it should be atomic, but you don't increment it with a fetch and add, but just, so how do you make the interleaving happen between?
Yes. So the question was about, effectively summarize, when we can preempt things. Anytime, it's good. We have full control over it, basically. So we can cut the slices down, which helps, but we also have a K-func called eBPF kick CPU that kicks the CPU quickly, which is pretty cool. How we'd integrate that is a different question. We haven't done it yet. We're purely working with slices at the minute. So that does, that does get the preemptive scheduler to kick in and stop the process. And we will get these interleavings eventually. But yeah, having a more, if you could look at the memory and see a bit that's flipped and then kick it, we have that option, which would be very exciting in the future. I'm hoping that we've opened SCEDX to the world of testing and that everyone will have great ideas now. Because, yeah, I'm a scheduler developer. Johannes is an OpenJDK developer that likes schedulers. So it would be really cool for other people to see that schedulers are available to them and not completely impossible to write now, and use that in testing more widely.
Can you prevent the soft lock from killing Linux? If, let's say, you want to explore all possible schedules which can occur in the system, but then it will crash.
So there's 2 parts to that. We have 2 of these kind of lockup detectors. I glossed over it earlier, but SCEDX itself, if you were given a task that's runnable and you wait more than 30 seconds and don't run it, the SCX scheduler will get kicked and all those tasks will move back to the fair scheduler in the kernel. There's also the soft lockup detector, which happens a bit later, that if the machine isn't, I'm not super sure on the details, I just know we hit it. If the machine isn't making reasonable progress, and it's not much later, I think it's maybe 40 seconds, 45, then it just reboots the machine. And that one, I would say turning that off probably isn't super productive, because if you were to hit that with any normal schedule without your scheduler, the machine would do the same thing. The SCX one, we haven't needed to turn it off, because 30 seconds is such a long time. Technically, if we were making kind of network requests, they could take longer to come back than that, but for the vast majority of bugs, 30 seconds should be plenty. If you do want to change it, there's a number in the kernel, and you can always recompile it, and that will get longer. But you've got to be, there's many systems that come in to make that stop.
One more question.
Is there any sorts of other erratic behavior that you guys have tested aside from like delays in scheduling, like overloading an ESQ or too aggressive preemption?
Yeah, that's a good question. The question was about more erratic behavior instead of just scheduling timings. The short answer is no, basically. There's stuff we're interested in, like memory latencies change on systems as they get more loaded. We haven't done any work to try and cause that yet, and it's not easy to do that with the SCX scheduler. There are ways to do it. You can kind of force things to mess up their caches more often with scheduling decisions, and introduce extra processes that do that too. But I think those races are a lot finer grained, and we haven't started looking at that yet. That's great. Thank you very much.
Thank you very much.